Okay, hello, welcome everyone, both those of you online and those of you here in person. Welcome to our training for Savio. This is sort of designed to be an intermediate level training where we cover topics related to the Slurm scheduler and to Conda/Mamba environments. I did see that a number of you, when you signed up online, said that you were sort of fairly new to Savio. So hopefully we'll be able to cover both aspects of the topics that will be useful to folks who are newcomers and aspects to folks useful to folks who've been using Savio for a while. Hopefully we won't fall into sort of the pedagogical valley of death where we go too fast for half of you and too slow for the other half. Okay, so we'll have two presenters. I'll be presenting the Slurm part of the session, and Jeffrey, who should be arriving shortly, will be presenting on Conda and Mamba. Both of us are consultants with Research IT and help support use of Savio and some of the other services that Research IT provides. So just a little bit of sort of background on sort of some things that are going on, a little bit ahead of time, but there's going to be a training on cybersecurity for researchers in October you might want to be aware of. And then if any of you are grad students, we have appointments. We actually hire grad students to serve as consultants, and indeed Jeffrey is one of our graduate student consultants. So if that might be of interest to you, please get in touch with us. Okay, so we'll do this in part as a demo, in part with slides. You're welcome to log in and sort of try out the examples as we go along. Please also, if you have questions as I'm sort of talking through specific topics, feel free to ask those questions, or you can wait with sort of potentially more general questions to the end. And you're also free to post questions in chat on Zoom, and we have some folks monitoring the chat who can potentially respond to specific questions there. So we have a couple of tiny URLs here. The actual materials are on the GitHub repository, and that is this tiny URL, brc-April 24. And the actual, I thought I had linked to the actual, to a website version, which is just tiny URL, brc-24-web. But in any event, you can get the materials there. Actually, oh, I know. I guess I sent that out in email in advance. Okay, and then just a reminder of how you can get help with Savio or with Research IT related topics in general, both through our mailing list here, which goes into the Savio ticketing system, or more general questions that are not Savio related. We have various email addresses you can use to get help both with computing and with data management, as well as our status. Okay, so like I said, I'm going to cover the Slurm topic, and Jeffrey will cover the Conda/Mamba topic, and you can see some of the things that we'll talk about here. Okay, so let's see. Just to start off, I just want to give a sort of brief intro to sort of what is this idea of scheduling. Hopefully, a number of you are already familiar with this, particularly if you're already using Savio, of course. So the scheduler is the software that basically manages the fact that hundreds of people are submitting jobs to Savio, and it needs to basically balance those submissions with the actual hardware resources that are available, both the nodes and memory and GPUs as well. So we use the Slurm scheduler, which is a particular software that does scheduling. There are others, but Slurm is quite popular to basically allocate access to those compute resources for all of the various user jobs, start and monitor those jobs, and basically manage the queue and decide who gets to be the top of the queue and who gets to be further down in the queue. So when you are connecting to Savio and submitting jobs, you are the user here. You're then connect via the internet, either via SSH, just in a simple terminal session, or potentially you might be going in through the Open On Demand portal, ood.brc.edu, which also allows you to start up a terminal in Open On Demand. Or in some cases, when you're using apps on Open On Demand, they will also be behind your back submitting jobs to the scheduler on your behalf. So when you connect via SSH or a terminal in Open On Demand, you're going to be on one of the login nodes, which are these 4 cylinders here. There are 4 different login nodes. And then anytime you actually want a compute node to do computation, you are going to be submitting jobs through the scheduler, either with the sbatch command or the srend command. Depending on what resources you request, you're then going to get allocated one or more cores or CPUs and one or more nodes of the cluster. So each of these little cylinders here is meant to represent a separate machine, or what we would call a node in the cluster. And each of these sort of groups of cylinders are the different partitions. In principle, each of these partitions is made up of machines that are all of exactly the same type. There are a few caveats to that we'll talk about a little bit further along. And this is a rather old slide, and so some of these partitions, like the Savio partition, no longer exist, and we have newer partitions like Savio 3 and Savio 4 that are not shown on here. Okay, so the first thing to sort of be aware of as a user is that when you're submitting a job, you're submitting it via what we call a Slurm association. An association is a combination of the account you're submitting under, which is either generally going to be a condo or a faculty computing allowance, and the partition that you are submitting to. And any individual user may or may not have access to a given combination of account and partition at a given level of priority to that partition under that account. So just as an example, here I'll just switch over and show you it live. You can check and see what associations you have available to you, what combination of accounts and partitions with this invocation here. And of course, you'll want to plug in your own username. And so what we see here is there's sort of a long list of the different combinations that I have access to. There are more here than you probably will have access to, just because I have access in a variety of different ways. But the ones that are going to be most common and most relevant for you are, you'll probably see either a set of associations under a faculty compute allowance or under a condo project. So if we highlight the ones that are associated with a faculty compute allowance, and that's what the FC stands for here at the beginning of this, the name of this account, you'll see that essentially for all of these lines, you'll see that I have access at normal priority to these various partitions. The right-hand side here is the default the default access level that you have, and the queue that you have access to, and the second one inmost here is all of the various queues that you have access to. So you can submit to sort of at normal priority or at to the debug mode, which will often get your job started faster, but is for a shorter period of time. And then in some cases, you can request access at low priority into the low priority queue. So most of the time, if you're using a faculty compute allowance, you'll just be using Savio normal, which is the default queue, and gives you sort of normal priority access, and that's what's indicated. Now, if we look instead at an association that involves a condo, so I have access to a condo associated with the statistics department, what we'll see is that the picture is a little bit different. In most of these cases, I only have low priority access to most of these partitions. So all of these Savio 3 and Savio 4 partitions, I only have low priority access to. And that's because our condo didn't buy any nodes that are in those particular partitions. In fact, the only nodes that we bought were Savio 2 GPU nodes, which are listed here. And we also bought some Savio 2 nodes, which are listed. That's odd, but anyway. So what we see here is that I do have regular normal priority access to the Savio 2 nodes, because those are nodes that the condo that I belong to purchased, whereas I only have low priority access to the other. Okay, so questions so far? And I should have said, if anybody has questions online, feel free to just speak up, or as I said, to ask them in the chat. Okay, so going back to the slides. One of the things that you might see if you submit a job to an account partition combination that you do not have access to is that you will immediately get this response. For example, in the stat condo, I don't have access to Savio 3 extra large memory. That's because there are a very small number of nodes that are in that partition. And so, well, actually, there are different reasons going on here. But the main thing to say here is that this is the message you will get if you don't actually have access to the partition and account combination that you asked for. Okay, so next let's turn to actually submitting a job, presumably to a partition and account that you have access to. So just to see sort of the basic structure of a job submission, this will be a batch or background job submission. So I'm going to create a shell script that contains some comments that have the information that I want to pass along to the Slurm scheduler, and then at the bottom, the actual code that I want to be run as my job. So all of the stuff in comments up here that starts with a comment character and then sbatch is basically setting a Slurm flag that's going to control what kind of resources that I'm requesting. And that will also just control some of the information about sort of how information gets passed back to me and so on and so forth. So I think we see here that I'm optionally setting the name of this job to be test. And then most importantly, I'm setting the account to be my faculty compute allowance, the partition to be Savio 3 HTC, and that I'm asking for 2 CPUs or 2 cores on a single node. So by default, I haven't specified, because I haven't specified it, I'm going to get these cores on one node, and I'm only requesting access basically to one node and 2 CPUs on it. So then a common pattern in your code is you're going to load one or more modules, and then you're going to invoke the executable that you want to run. Might get more complicated than that, but this is sort of the simple case. So in this case, I'm just going to run some Python code. All that this Python code does is a fairly intensive linear algebra operation. The reason I'm doing it this way is I want to illustrate the fact that I'm getting access to 2 cores and that we could actually see the job running on 2 cores. So let's actually submit this and see that that is indeed the case. So let's just check that I've got my job script here. So it's this test.sh. And now I can do sbatch test.sh. And it says it submitted this job with the job ID of 181.14571. And we can see that it's already running. Sometimes you might see that it's pending, but in this case, we see that it's indeed already running. So one thing I could do just from the outside is just see what amount of resources are being used by this job. So this wall command is handy for that. That says it's no longer running, apparently. I get the, I think I probably job. Oh, okay. So you'll see that it is using about, let's see, this is in megabytes. Not using 174 gigabytes, so might not see here. Also, shouldn't be using 23% of the CPUs. Let's actually log into the job and see if we can see things that way while I try and collect my thoughts and see what might be going on here. Oh, what's probably the case. This is what. Okay, so I think this is in aggregate over all of the different users of this particular node. And so that's why it's looking like it's using a lot more CPUs and a lot more memory than I would have expected just for my job. And what I meant to do was srun. Okay, so in all that time that I've been talking, the job finished. So let's just check that again. Okay, so I'm going to submit the job again. And now I'm going to do srun -- job ID with the name of that, the new job. And I'm going to request a terminal on this node. And now I can do things like run top and actually see what's going on with my job. So we see here that my job is the one that has 198% of CPU, 199%. So this is because I requested 2 cores and my code is actually set up to be able to use 2 cores because our Python installation by default will run its linear algebra using 2 threads, which will end up using 2 cores. So logging into the node and then using tools like top or free to look at memory is a nice way to see if your job is behaving the way you would expect. And in particular, if you're running parallel code or think that you're running parallel code, to see if it's actually running in parallel and whether you've sort of set things up correct. Okay, so this has all sort of gotten a little wonky because my job ended, so I'm just going to hit Control-C to get out of here. Okay, so questions or comments at this point? Okay, so we already saw some of this in terms of monitoring things. You can also use this saccount command at the bottom to take a look and see sort of what the details of your finished job were, if you want to go and look and see how much memory was used at maximum or how long it took to run the job and so on and so forth. Okay, so next I want to turn a little bit to sort of requesting resources and sort of trying to troubleshoot problems that might occur immediately upon submitting a job. Before we get to that, let's just talk a little bit about resources. Some of the nodes on Savio are scheduled on a per node basis. So if you request access to if you start a job on one of these partitions that is scheduled on a per node basis, you're going to get the entire node whether you ask for the entire node or not, and you're going to get charged for that entire node. More recently, most of the newer partitions have been set up to be scheduled on a per core basis. And for that, you're going to request as many cores or CPUs as you would like on the machine. And so you could request 4, you could request 24, you could request the entire node, or you could request a subset. And one thing that is important to remember when you're requesting by core is you're going to get allocated the amount of memory proportional to the number of cores that you requested out of the total number of cores that are on the node. If you want more memory, I think this is on the next slide, if you want more memory, you should request more cores. And that's sort of how we handle charging for memory usage. One thing that I won't say too much about, but just to keep in mind, is I said before that for the most part, these partitions are made up in a homogeneous fashion of all the same kinds of nodes. That's almost true, but it's not quite true in that on some partitions, some of the nodes are a little bit different from each other. This particularly holds for the GPU nodes, but it also holds for some of the non-GPU nodes partitions. And so, for example, in Savio 3, we have some of the nodes have 40 cores and some of them have 32 cores. So if you wanted to specifically request access to nodes that have 32 cores versus 40 cores, we do have this Slurm flag that's called a feature, which is this -C flag. And if you look in our documentation, what you can see is that we'll sort of show you in our table of hardware that some of the Savio 3 nodes have 32 cores, some of them have 40. And on a different page in our documentation, you can actually see how it is that you would request access to particular hardware types. So that is under this node features column on this particular page of our documentation. And so here there's the Savio 3 or Savio 3 C40 feature, and that distinguishes between 32 cores and 40 cores. So some details here that you would need to look into, but just mainly just to sort of give you some awareness of the fact.
Chris, we have a question online. Somebody's asking how to request 40 cores using batch.
Oh, it's all the same. Yeah, I should have said that what I showed you a minute ago was with SBatch, and you put the pound sign and then SBatch and then the flag. Here I'm doing it in an interactive job, but it's basically all the same. You just put -C, Savio 3, C40 as one of the lines with the comment in the batch job. So the flags are exactly the same. It's just syntax is specifying them with the comment versus just directly. It differs a little bit. Okay, I mentioned memory, so maybe I don't need to say anything about that here, anything much more about that here. You don't need to request any particular amount of memory. If you're getting a whole node, you're going to get all the memory on that node. If you're requesting a number of CPUs on per core partitions, you're going to get proportional memory. If you want more memory, request more cores. That's sort of the end of, more or less the end of the story here. GPUs get to be somewhat more complicated. Part of the difficulty here is it's hard for us to keep up with the technology and at the same time have partitions that have a sufficient number of nodes and are all the same type of GPU. And so in particular on Savio 3 GPU, we've got 4 different GPU types, which is a little bit frustrating from our perspective and probably from your perspective, but that's sort of the way the world is these days. So when you're requesting GPUs, you actually need to sort of request a number of different details. You need to request the number of GPUs. You then need to request a certain number of cores for every GPU that you request, and that number varies depending on which GPU type you're asking for. And we document that in our documentation. And for Savio 3 GPU and Savio 4 GPU, you need to actually say exactly what kind of GPU you want. And so what that means is that, and I see there's a typo here, this was supposed to be srun, as it was on the previous command, but these flags would be the same in SBatch. Is going to request the Savio 3 GPU partition, for example, and then via this -/grez flag, you're going to be requesting the kind of GPU, in this case GTX 2080 Ti, the number of GPUs, in this case 1, and then the number of cores that go along with that GPU type on the number of cores per GPU, or sorry, the total number of cores that you need in order to have the right number of cores per GPU. So in this case, for these GTX 2080 Ti's, you're supposed to request 2 cores per GPU, so I'm setting -C to 2. If I were to request 2 A40 GPUs, you're supposed to request 8 cores for every A40 GPU. So in this case, I'm requesting 16 cores just from 8 times 2. Okay, and then if you're requesting multiple GPUs, then Slurm is going to set this environment variable CUDA visible devices. I just found out recently, I thought that these would be numbered 0, 1, 2, 3, and I found out that's not necessarily the case. This slide needs to be updated a little bit. But in any event, I'll say a little bit more about this CUDA visible devices a little bit later.
Chris, we have a question in the room and
thanks.
online.
I was just wondering, like, for say Savio 3, how would you select which of the GPUs of those 4?
Yeah, you would need to get some sense of what kind of job, what kind of task you're running and what GPU is suitable for that. One aspect of that might be how much GPU memory you need, because these different GPU types vary by but that would actually come from some domain knowledge, or maybe some of your colleagues have some sense of like how well a job has run, a particular kind of job has run on different GPUs.
And then the other question is, what's the downside of requesting fewer cores per GPU than the recommended ones?
The downside is your job won't start. That's the downside, because we won't actually be able to bill for your usage in the way that we want to. We'll actually see what happens in a moment. Okay, so there's sort of two things that can go wrong at the point of submitting a job. One thing that can happen is your job could immediately fail, and you could get a hopefully generally informative message saying what's wrong. One of those could be this thing that we already saw about the invalid account or account partition combination. Another could be that you have run out of service units or credits in your faculty compute allowance. And what you should see in that case is a message that this user account here does not have enough service units. And if you then want to go make sure that that is indeed the case, you could use this check usage command. And with your FCA, this is just an arbitrary FCA that I chose. And this one, for example, has an allocation of 300,000 service units, and it's only used up 7,800 of those service units. So this account would not get that particular error message. And also, if you're up at like 290,000 or 299,000, and you request a time limit and number of cores such that you would go over the 300,000 limit, your job also won't start. Yes.
So somebody's asking how to check GPU utilization. I believe you just.
Yeah, I'm going to come back to that in a minute. It basically involves logging onto the node and running the command NVIDIA SMI. So we'll see that a little bit at the end.
And then would the provided commands be good starting points if you're running a GPU command for the first time?
We'll get to that in a little bit. Yeah. Okay, so some of the things, another set of things that can go wrong is you submit a job, Slurm doesn't tell you anything has gone wrong, and your job never starts. These are fairly frustrating and the source of people writing in and asking us what the heck is going on. So I've tried to sort of categorize a number of things that can happen and what they look like. Here's a case where I requested a job to run for 74 hours, which is above the 3-day, 72-hour limit on regular faculty compute allowances. And you will see this QoS max wall duration reason for why the job is not starting. And it'll just sit in the queue forever. So that's something to be aware of. If you request too many nodes, like here I'm requesting 40 nodes, which is more than the maximum number of nodes we can request under a faculty computing job, you will see this QoS max node per, probably per job limit. So that will be something that can happen. Back to the GPU question, if you request fewer cores than you should for a given GPU request, like here, you're going to see this QoS min CPU not satisfied reason for the job not starting. And then you can also end up with a message that basically says that you haven't requested a GPU, or potentially requested a GPU that there is no GPU of that. That would be this QoS min gres. So these are all things to look for if you've submitted a job, but it seems like it's never starting. You can look and see these reasons. Okay. Let's see. Yeah, so I showed just in here some of these indications to look at the queue. I just want to say a little bit more about that before we go on. So SQ is the command, is one command that's quite helpful for trying to understand what the queue looks like, why your job might be starting, where your job sits relative to other jobs that are in the queue. There are a huge number of options for output that you can get from SQ, and so I've got sort of a particular invocation of it with all of these different requests of what it will print out. If you do look at the man page for SQ, you will see all of these. So you can do like man of SQ. And then if you hit the space bar to sort of page down, eventually you'll start to see sort of all of the different output flags that you could give. In fact, if I hit / and -O, I should see this. Anyway, I don't want to go into too many of the details here just for the sake of time. but I will paste this in so we can. Oh, it looks like I got kicked off of. So I'll do it here. And you can see that it is sort of showing all of the jobs for lots and lots of different users. You can see that here's a person who submitted a job implicitly via Open on Demand, and it turned out they requested that the job run for too long, so they're getting this max wall duration problem. But you can also, sort of see how many jobs are running in the different partitions, how many jobs are queued, et cetera, et cetera. One of the things to keep in mind, which is a little bit awkward to see here, is that this priority column basically says what priority your job has relative to other jobs that are in the queue. And I'll say a little bit more about how that number is set in a bit. Okay, so let's suppose you've submitted a job, you haven't gotten an error right away, you aren't in the situation where the job is just hanging forever. And you want to know why your job might be sitting in the queue. So a few different ways to go about that. We have a tool called SQ, just the letters SQ, that you can use, which is basically a wrapper around the SQ command meant to provide sort of user-friendly output. You could also simply go and look and see how heavily used a given partition is. So I could, for example, say, do this for Savio 3 HTC. And in this case, it says, oh, many of those nodes are fully allocated, 14 of them, and 10 of them are in a mixed state. So if you submitted a job that requested a fairly large number of CPUs, this might be the reason why that there isn't the Slurm can't give you access to those cores because it's not able to find enough cores on a given node relative to the usage from other users, for example. And you can use this SQ, the full word SQ command that we've been seeing already. So some of the reasons that your job might start and that you might see in the column that is the reason column for why the job is queued are priority and resources, which basically, both of them basically amount to the fact that your job is sitting in the queue because there aren't enough resources available for your job to start yet. If it says priority, that usually means you're below somebody else in priority. If it said resources, that will often mean you're at the top of the queue, but they're not quite available for you. There are these reasons that are about CPU and node limits that can pertain both to a condo being full of jobs such that your condo job can't start because the other people in your condo are using up the entire condo, or in some cases because of basically a faculty compute allowance, because collectively the faculty compute allowances are using up all of the resources that they have access to in a given partition. And then the other thing that comes up sometimes is this requested node not available reserved for maintenance. This will often be the case if there is a downtime scheduled and you're submitting a job where the time limit of the job would overlap with the time of the downtime. So the scheduler is basically going to wait to start your job until after the downtime is complete, is over. So let's go ahead and just quickly look at just to get a sense and see that we can sort of see some of these things going on in the queue when we. So I'm gonna do that, and we can just sort of page down through here and see if we notice anything useful. So here we see that this user Sang-Yoon has a bunch of pending jobs, and we can see that the user is those jobs are not starting because of this QoS group node limit. So what that presumably means in this case is this particular condo, which is not listed here. It looks like maybe I haven't printed out the name of the condo account. But whatever condo this job is being submitted to, other users in that condo, perhaps the same user, have a bunch of jobs running in the condo. They've basically used up the allocation of that condo in terms of how many nodes and cores were purchased by that condo. And so this user's jobs are now waiting in the queue until other jobs in that condo end such that this user's job could start. Yeah.
Related, somebody's asking, how can we know the limit of resources for FCA, faculty compute allowance? There are usually only limits in terms of some of the smaller partitions have limits that the FCAs can't use up the entire partition. I don't remember off the top of my head how to check that, unfortunately. Maybe one of my colleagues can answer that. Okay, so that was a little bit about sort of using SQ to sort of see what's going on. You can also use the SQ command, and that will show you some hopefully user-friendly information. In this particular case, I don't have any running jobs, so it's not going to show me anything about the running jobs, but it will show me something about the history of my completed jobs and whether they failed and maybe some indication of why they failed. And I could actually, in this case, run it for that user who we noticed that some of his jobs were queued. And so let's see what we see for this person. Okay, so maybe that person's name is not actually. So that person's name is. So that's their that I think is their username. Okay, so they've got a bunch of jobs running, and there's some information here saying this job is waiting until this QoS has available resources. This particular kind of QoS is associated with a condo, and so that basically means the condo doesn't have available resources. See if there's anything else. So it looks like this person has a lot of jobs running, or a lot of jobs queued. And so, yeah, we can indeed see that sort of similar information is shown in tabular form as well. Okay.
Just
Yes.
following up on that previous question, Mark answered that you can use the check usage SH tool for that. And you can also track service unit usage via the MyBRC portal.
Yeah, I think the question was not about, I could have misinterpreted. I think the question was, well, I'm not sure. I'll leave it at that. Okay, a little bit about how the queue works and which jobs will start before other jobs. So the queue works according to two principles called fair share and backfilling. Fair share is basically a mechanism by which the scheduler determines whether I have a higher or low priority for my job than you have than your job that's been submitted. And that's basically going to be determined by how much usage there's been in my faculty compute allowance compared to the faculty compute allowance that you're using. So if a lot of people have been using my faculty compute allowance and very few people have been using your faculty compute allowance, your priority should be higher than mine or anybody who's using my faculty compute allowance. And then for people within a faculty compute allowance, there's also then sort of in a hierarchical fashion, there's some prioritization based on how much you've used versus how much your colleague has used. So that's basically fair share. And that's sort of in addition to the fact that the condo jobs will get higher priority than faculty compute jobs as well. The other principle is backfilling. So the way that Slurm basically works is you can imagine that we've got 6 nodes on the cluster, and suppose these are the jobs that are currently running. And so based on the time limit that you give to a job, Slurm is basically saying that it expects the job to last exactly that long. And so it's going to, if at this point in time, there are 5 jobs running in these dark orange here, and there's sort of open resources here on this first node. Well, what happens is if this 2-node job has the highest priority amongst the jobs in the queue, Slurm is going to say, well, based on the time limits of these other jobs, I'm gonna plan to run this 2-node job on nodes 1 and 2. Now, in some cases, it might end up, I think it might end up putting it on a different node because the other jobs might finish not exactly at how long their time limits are, but this is how Slurm is thinking about setting up the schedule, the queue. And so what that means is that there's sort of this empty resource that's available for this single node for this amount of time. So if Slurm can fit your job into one node and that short amount of time, it will start your job and allow it to run before the job that has a higher priority. What it will not do is if your job needs to run for longer than that short window, it will not start your job because it's not going to allow your job to interfere with this higher priority job starting later than it thinks that it should start. So that's this idea of backfilling. It tries to sort of slot in jobs as best it can, but but it's only going to slot them in if it thinks that it can slot them in without slowing down the starting of other jobs that are already higher up in the queue. Okay, so a little bit more about the queue in terms of condos. I think I basically said all of this. Condos are limited to the amount of resources that were purchased. Additional jobs on top of that will be queued. And the jobs within the condo will be ordered based on this fair share scheduling of how much different users have used. In some cases, a condo job might not start immediately, even if the full condo amount of resources is not used up. And that could be because fact, the compute allowance jobs are using up all of that partition, or in combination with other condos are using up that partition. So the condo jobs will be at the top of the queue, but they may still need to wait for resources to become available. In the FCA, it's really more about just how much one FCA's usage has been recently compared to how much a different FCA's usage has been recently with this fair share scheduling. Okay, so if you want to know when Slurm expects your job to start, that will also be listed with this SQ tool. If you want your job to run faster, there are a few things that you can do. One is that you can reduce the time limit and request fewer nodes or cores if that seems plausible for your job, which in many cases it wouldn't be. But that would, for one thing, that would allow your job to potentially fit into this backfilling process that I described. Another thing that can be quite useful is using the sinfo command to see if you can find a partition that is less utilized than some other partition. And we sort of saw that before with, we saw, for example, that Savio 3 HTC was quite heavily utilized. But maybe we could see if Savio 3 has more available nodes. No, Savio 3 is quite heavily allocated now. So what about Savio 4 HTC? Well, that has 4 idle nodes, so maybe you'd be better off submitting to Savio 4 HTC than to Savio 3 HTC, for example. And then you can play games with deciding if you have access to both a condo and an FCA, you can play games with submitting to the condo versus the FCA, depending on whether the condo is sort of fully utilized versus whether or not, versus the fact that you'll get a higher priority in the condo. So that can trade off in different ways depending on what the queue looks like at a given time. Okay, so I'm going to close by talking a little bit about parallelization, then a little bit about sort of troubleshooting jobs that fail. So with parallelization, there are sort of a number of different ways that parallelization can work for a given code that you're running or a given executable. And those can sort of map onto how you request resources from Savio in a variety of different ways. So you might be requesting resources that just use a single node and that use threaded code, things like OpenMP or threaded building blocks. You might be doing, for example, threaded linear algebra, either with or without knowing that, in Python, in NumPy, or in R or Julia. That was the example that we saw before. You might be running on one or more nodes where instead of using threaded code, you're going to be starting up multiple processes as part of your job. So that could involve various tools in Python or R or languages like that, where you can run loops or map operations in parallel, and that will generally start up basically one process. You'll have multiple workers. Each worker will be a different process on the computer, and those will often be using just a single core. You can also either directly yourself be using MPI, or you could be using some code written using MPI to take advantage of running often across multiple nodes. Or if you have a number of different jobs that just use a small number of cores, you might want to aggregate those jobs into a single job and run that across one or more nodes. And that would be often done with this tool called GNU Parallel. So these are some of sort of the modes that people would be using. And then, as I said, lots of different executables will use some of these different tools sort of behind the scenes. So some of the sorts of things that you might be doing is running multiple processes. You generally want to have one core per process or multiple cores per process. You generally don't want to have one core running multiple processes. You will often have, for example, in Python or R, you often have a number of worker processes, and then you might have one or more computational tasks that you're going to run on each of those workers. The term task can sometimes get a little confusing because in the context of MPI, it basically means workers. But in sort of other contexts, you can just sort of think of a task as being a computational operation that you want to do. And then the other thing to keep in mind is whether or not the executable that you're running is actually set up to run in parallel. So in some cases, it might be able to run in parallel without you sort of doing anything. And that will be the case in some cases for, like I said, the linear algebra in R and Python. But in many cases, your code is only going to run in parallel if you determine, first of all, that it can use parallelization, and second of all, if you tell it to run in parallel via various flags that you would pass into the executable. Okay, so in terms of the flags that you would specify to Slurm to get the resources that your code could then take advantage of, there are a few different flags that get used in various combinations. So minus CPUs per task basically says how many cores do you want to run for each task, whereas minus n tasks is the number of tasks you want to run. And then you could also instead specify the number of tasks per node and then the number of nodes that you want. And based on you having set one or more of these, Slurm will set the others by default, often to the value of 1, and it will set these various environment variables that you could then use in your own code in your JavaScript. So how do you decide whether to use the CPU's flags or the n tasks flags or the nodes tasks? The nodes flags. So you can either use CPUs per task or n tasks to get multiple cores. But there are a few caveats to doing that. So one of those is if you use minus CPUs per task, you're not going to get cores spread across multiple nodes unless you request multiple nodes. The other is if you just request minus n tasks, it doesn't actually guarantee that all of the cores that you get are going to be on the same node. So that can sometimes determine how you decide which of those flags to use. And then the other is that if you are using MPI or any code that uses MPI, you want to use n tasks because n tasks in Slurm language masks onto the MPI tasks or ranks for MPI-based code. And then if you're running code where you're going to be running, say, multiple processes and each process might be threaded, then you would want to specify both CPUs per task for the threading and n tasks for basically the number of different workers that you'd be running. Okay, so some of the examples that one might find are one node, many cores, many nodes, many cores, or hybrid jobs where you have many tasks and each of those tasks is using multiple cores. And so just to briefly show a few of those examples, I'm running a little low on time and I should switch over to Jeffrey quite soon. Here's an example of running some threaded code where you say, I just want one node, one task per node, but I want 4 CPUs to be able to run those threads on. And in fact, you don't even need to specify the nodes and n tasks per node because that's going to be 1 by default. In contrast, here's a situation where you might want to run 20 different worker processes. So you might specify that as 1 node and 20 tasks per node with 1 CPU per task. And here's an example of using MPI where you want to use n tasks. And so here I'm specifying that I want to run 40 MPI tasks. And by default, when I use MPI run down here, it knows based on what was set by a Slurm that it's supposed to use 40 different MPI tasks or ranks. And then here's an example of a hybrid job where suppose you were using MPI, but for each of the MPI tasks, you're going to use multiple threads. So then I'm going to say I want to run 2 nodes, 4 tasks per node, so a total of 8 MPI tasks. But each of those tasks, I'm going to use 5 different cores here. Those are some of the kinds of combinations. Okay, so then I think I'll sort of skip over this about MPI. There's some troubleshooting tips for MPI, which basically amount to trying to make sure that the version of MPI that you're using when you compile code and when you run it is the same. And if you're using a container, that the version inside the container and the version of MPI in the system are the same. So those are often the things that will be problems with MPI. I guess I was hoping to have a little more time to discuss this, but if you submit a GPU job, this is just an example of just a very basic use case where you could actually submit a GPU job, request 2 GPUs, and then use both of those GPUs, in this case using PyTorch. Here I'm just moving data to 2 different GPUs. And back to the question that was asked earlier on, if you want to make sure that you are actually using both GPUs, once you start your job, you can then use that srun minus job ID to get onto the same node that your job is running on. And then you can run the NVIDIA SMI command to see about usage of those GPUs. Yes.
Does the generic guide on using like parallel training, like that was usually done on PyTorch geometric work with the Slurm setup, or is there something that I should watch out for when I sort of port things over?
I suspect it would mostly work. I'm not familiar particularly with that guide. You're basically, the main thing is just to make sure that if you're requesting multiple GPUs, that your PyTorch code is then set up to take advantage of those GPUs.
Gotcha. It's the data parallel thing, but yeah.
Yeah, I'm actually not sure of the details of that. Okay, so-
Another question, Chris.
okay.
If we request one GPU in a node which has 4 GPUs and use NVIDIA SMI to check the GPU usage, how do we figure out which GPU is our job?
Yeah, you're going to need to use top or the PS command to figure out what the process ID is that is associated with your job. And then in NVIDIA SMI, then you can see the process, you can see which GPU is associated with that process and then see the memory usage and the GPU usage of that GPU. Okay, so just wrapping up quickly here. If you have a job that seems like it's not behaving the way you wanted to, or it actually failed, some of the troubleshooting tips that I would generally give, and these are the things that I go through if I get a user request, a ticket coming in and I'm trying to figure out to help the user what might have gone wrong, is I try and look at the output files, either .out or .error for that particular job. I try and use the saccount command, and I have sort of some indications here that will give some information about how that job behaved, how long it ran, how much memory it used. There's sometimes a failure code in there that occasionally is useful. You can look and see what node it ran on, and if you've submitted multiple jobs that all failed and they all failed on the same node, there's a chance there might be a hardware problem on that node. And you can actually then rerun your job either excluding or including that specific node and try and see if you can reproduce the error based on the node. You can also use srun, where you actually manually run the same code that you were running via your sbatch command, to try and see if you can actually see the output and error messages, or see at least on what line of your code things are failing. And sometimes if you've got a multi-node job, you might want to try running it on a single node to see if the problem is the communication between the nodes, or if it's something more fundamental to the job you're running. Okay, so let me stop there. Any questions before we switch over to Jeffrey and the Conda stuff? Yeah.
I have one question. How many jobs are we allowed to submit at the same time? Somewhat.
Yeah, you're allowed to submit a reasonably large number. If you submit thousands and thousands of jobs, the process of doing the scheduling will slow down. So I'm not sure I have a great exact answer, but I would say if you start to get above a few hundred, you probably wouldn't want to be submitting in the thousands or tens of thousands, but certainly dozens or small hundreds is
yeah, small hundreds is fine. I was thinking about if it's 50 or 100.
Good. Questions? All right, Jeffrey.
Thank you to Chris for that amazing presentation on Slurm. I'll get started with the Conda Mamba presentation. This will be interactive like the last one as well, so you guys can follow along. So first, what exactly is Conda? It was created in 2012, right? In Python, data science, the biology community, they really had a problem with package dependencies. So Conda was created as an open source solution. So it's pre-installed on Savio, but if you are installing it on Conda, you can pick between mini Conda or Anaconda. The real difference between these two is mini Conda is around 400 megabytes and Anaconda is around 4 gigabytes. Anaconda comes with a cool GUI and more core features, but for the real core features, mini Conda should be okay. And Conda is used with a lot of programming languages, but we most often see it with Python, and it can work across multiple platforms. What are Conda environments? Okay, so one of the big features of Conda is Conda environments. So Conda environments let us work with different versions of the same package. So we can kind of see from the picture that we're working with this program called Sauron, and it requires a very specific set of versions for the packages involved in it. And person one is the person who created Sauron and created it with these packages in mind. And person two wants to work with this. Instead of having to go through and dig and see which versions of packages they need to install, a simple solution is just to create a Conda environment and transfer it over to person two to allow a seamless use of this program. So what is Mamba? So one problem with Conda that we often see is it can be slow. So Mamba attempts to remedy this problem. It's a faster drop-in replacement for Conda, which is implemented in C++. Conda is Python, C++ is a lot faster, and it uses parallel loading. So Conda and Mamba, they can really just be used interchangeably. Once you download Mamba, you don't have to worry about whether you use Conda or Mamba as your command. You can just use either or. So Savio is upgrading its operating system to Rocky 8. So after the upgrade is finished, you can just type this command on the bottom, and then you'll have Conda as your default solver. You shouldn't really have to do this one at the top.
Maybe you'll have Mamba as your
Yeah,
default.
you have Mamba as your default solver, sorry. And then you shouldn't really have to do this one at the top, but if you're working on a local machine, you probably have to set Mamba to your default. So if you aren't convinced by all of that, a quick rundown of like the key benefits of using Conda environments: dependency management. You can work with different versions of packages. Reproducibility. This is extremely important in scientific computing. Our findings have to be replicated, and it has great integration with Jupyter Notebook. You can set up Jupyter kernels based on Conda environments. Collaboration. You can share your environments with others, and you can make sure everybody on your team is working with the same package. You can have a shared Conda environment, which people add to. And it's cross-platform. You don't have to worry about operating systems. So let's get started with the demo, setting up and creating Conda environments. So this is an example command of how to create an environment in Conda. In Savio, we first load the Python module, and I'm on login node 2 over here. And then
We're not actually seeing or we switch over.
grab this command first.
Can you share your window, like your screen?
Oh, sorry. Okay. Is there a way I can share two screens at the time?
Just share your screen and then it'll show whatever's on desktop. Just.
Okay. Yep, so this is the result of putting in this command.
Oh, I make it a bit bigger.
We see Conda pulling up all the packages. All we have in here is Python 3.10.
Can you make the type bigger?
The what bigger?
That's fine. Bigger command plus.
Now this is going to run. We have 23 packages with base Python. And then we can, of course, specify any number of package we want by putting an equal sign. So this is going to run, and then while this is running in the background, I have another shell open over here.
Yeah, bigger too.
Yeah. And we can see all the environments that I have installed. And then we see test environment, and then test environment 2, which is right here. See test environment 2. So you might have noticed that in our command that we used before, we had Mamba create -c Conda Forge. So what exactly is Conda Forge? So Conda Forge is where all of these packages live. So there are many channels. Popular ones include Anaconda, Conda Forge, and NVIDIA. And typically it's recommended to use the Conda Forge channel. Anaconda is kind of the official distribution. It's considered stable, but Conda Forge is really the community-driven distribution. And if you want to always have the most up-to-date packages, Conda Forge is a good idea. There's NVIDIA for NVIDIA packages, and there's also BioConda, I believe, which houses biology-related packages. So if we paste this command in, we'll set up in our Conda system to use Conda Forge as the default. So the main things that we do with Conda environments really are activating, adding to, and deleting our environments. So there are multiple ways to activate our Conda environments, and it's recommended to use source activate. Now, using source activate, you may potentially be greeted with a deprecation notice. That's normal, but it is a recommended way. The reason for this is because using Conda activate requires something called Conda init, which alters your shell, and it can cause it to slow down. If you do want to use Conda init, add this command in to stop it from slowing down your shell and modifying your base environment. So let's activate our environment that we just made. Now let's add to it. So you might wonder what this Flake 8 program I'm installing in the environment is. It's just a Python text formatter. I could have gone for something common like NumPy, but it's rather large and which takes some time to install.
Jeffrey?
Yeah.
Could you make your terminal a bit bigger for the font size?
Oh yeah. Is this good?
Do another increment. Bigger gradient would be better. One more.
One more? Okay.
Thank you.
Yeah. Sorry about that, guys. All right, come on, Mamba, you're supposed to do the fast one. There we go. And then we can, of course, deactivate our environment with source deactivate. You see a deprecation warning, ignore that. And then lastly, we can remove our environment. So while this is removing in the background, one thing to know about Conda is it works well with pip actually. Well, it's not well, but so pip is the alternate way of installing packages with Python. It pulls from the PyPy directory, which is a different open source system than Conda. So you can use pip with Conda, but this is not recommended as two systems handle their dependencies differently. So if you are using a Conda environment, you intend to work with Conda, it's generally recommended to use the Conda version of the package with Conda install rather than a pip install. But if you do want to use a pip install, it's key to isolate your environment. You want to avoid really affecting your home.local directory. So let's go back to our test environment 1 that was made before. And install Flock to it. Flock is just another lightweight package code formatter. Very lightweight, should install quickly. So when you are installing with pip, do not add the -- user flag, as when you install it using this flag, it's going to write to the .local directory, and your Conda environments have access to this .local directory, and we'll be using a non-isolated version of the package. So just regular pip install. And then we can do Conda list and see all the packages housed in our environment. And right here on this rightmost column, you'll see where it got this package from. If you see any .local or anything, your environment is not isolated, pulling from your machine's home directory. So that's an important thing to keep in mind.
I don't think it's actually going to say where it's coming from.
No, it's not.
I think you need to start Python and then import the package and do
package dot underscore underscore file underscore underscore to see where it's coming from.
Okay. Yeah, it's important to isolate your environment. That's one thing for sure. And then creating and using export files. So like I said in the beginning, like the collaborative aspect of Conda is like one of the things that makes it really popular. And this can be done by using export files. So we're currently in our Conda environment, and we can turn this into a YAML file. We can share this YAML file with anybody we're working with, and they can use that YAML file to recreate our environment. Let's see what's inside our environment file. And then these are all the packages that were in your Conda. You can see it captured the pip package as well. So now let's try something different and create an environment from a export file. So to do this, we can just create our file using touch. Then we can edit our file using nano. Just have to load that in. It's already loaded. Environment.
Question over here.
Going back to the installing packages with Git, I had a question with, I use a lot of packages that like aren't in Savio, aren't default in Savio, and I get really confused on where they're getting stored if I have multiple versions of something in multiple Conda environments. Like, are they all, where are they stored and all the?
Yeah. They should all be stored in the .conda packages. We're going to touch on that later in the presentation. Okay, it's going to run in the background. So deleting unused packages and creating Conda environments from scratch. So like going back to your question, so all of our packages all of our environments are saved to our local directory in the .conda folder, and we're granted 10 gigabytes of storage on our .local folder. So the exact location is our home directory .conda packages. And basically, like when you install packages and they're used in multiple Conda environments, Conda's smart. It doesn't reinstall these packages again and again and again. It caches the package and it distributes it to the different environments. So another quirk of this is when you delete your Conda environment, like we did earlier, it doesn't actually delete the packages because the packages are not stored in the environment. It's stored in .conda/packages. So it's proper form, best practice to clean out this place. So these are all the packages currently in my .packages. This is quite overwhelming, so Conda makes it simple. You can just do Conda clean -- packages, and it'll clean all your unused packages, right? All your environments that you've deleted, you're no longer using the packages, it'll get rid of those. Or if you want to just clean out the whole directory, you can just do Conda clean -- all. I won't be doing that here because it can take quite a bit of time. So yeah, that's a great strategy for managing your space usage and avoiding hitting that 10 gigabyte limit on the local. Of course, like this is oftentimes not feasible. You might have a lot of environments that you want to use and you can't get rid of them. So a great way to circumvent this 10 gigabyte path is to just save your environment in the scratch directory. Yeah, you can actually create Conda environments anywhere on your system. They don't have to be saved to .conda. You can specify a path using / prefix, and I will demo doing that right now. And I'll load. So to activate this environment, you can simply just add the path before your environment and prepend that to your activate command, and it will activate that. And a quick side note is to really just save you time and avoid using this prefix whenever you create an environment, you can actually just move your entire .conda directory to global itself. And then scratch itself. And then once you do that, you want to preserve your file paths and make sure everything runs smoothly. That is running in the background. That's the slide. So using an environment as a Jupyter kernel. So I was talking earlier how you can use an environment as a Jupyter kernel. On Savio, of course, we have open on demand, which is our way to use Jupyter. And when you click new, these are all your kernels right here. Right now I have this kernel called LLM docs, my environment. These are the pre-installed Python environments. So how do we get our new test environment into our Jupyter? So to do that, going on for the last thing, switch this terminal. Do that, we can activate our environment. In Python before we use source. Make sure that you have Jupyter and IPyKernel installed in your environment before you try to add it to Jupyter. I've done this beforehand to save us time. And then we can use this command to add our environment to our kernel. And then we can view all of our kernels with this command. And the test environment is now added to our kernel list. Our environment has been installed in Scratch that we were doing previously. Now let's go back to open on demand. And we see Python test, which is what we decided to call our new kernel. And then we can remove this when we're done with this environment and we no longer want to use it for this command. So .conda arc. So .conda .conda.rc is our configuration file, and it helps you, it allows you to customize how Conda behaves. So we can actually see it. Right here. So earlier we specified that we always use Conda Forge, and you can see that reflected in the Conda RC. So let's modify it now to do something cool.
Do you zoom in on this one as well?
Oh yeah, keep on forgetting that it doesn't do that by default. Here's our Conda RC. So NumPy is a pretty common package that everybody's probably going to be working with and should include in their environment. So let's modify our configuration file so that every Conda environment we create includes an NumPy by default. Copy this. Move that right here. And now every Conda environment that we create will have NumPy included by default. So lastly, closing up, all these examples that we've done have been in Python, but Conda Mamba is very useful for a lot more than Python. Really anything scientific or reproducible that you want to do is going to be a big thing that Conda can really help you with. So here's an example about how you can use it with R, and an example on how to use it with plus plus.
You're using like R Studio through OOD, are you able to access your content environment with R Studio?
Yeah, I believe so, because if you launch your R and Conda, you'll have all the packages from the Conda environment.
If you're using our studio, I'm not sure I think the wires might not be connected properly. If you're using a notebook that uses R, I think it might be fine, but
So it would have to be OOD, right?
using our studio, it gets more complicated in terms of setting the paths to where the packages are that are inside the content environment.
Lastly, how to get additional help. If you have any technical questions, feel free to reach out to our email or come to office hours. And yeah, thank you for listening to the presentation.
So we have some minutes in the back, and we'll be around if people want to ask questions in person. And I think a few of us may still be able to answer questions online if anybody has questions who is still on Zoom.